Hello friends, this is Subhash Jadhav. I welcome you all in our lecture series for Assistant Motor Vehicle Inspector Examination, in which we discuss about probable objective type multiple choice questions. In today's lecture, we will be discussing about engine cycles. So let us start. For the same compression ratio and heat addition, um, we are trying to find out which cycle will efficiency will be higher. So we have here three options, that is Otto cycle, diesel cycle and dual cycle. So preferably this is the formula, general formula for finding out the efficiency of any standard engine, that is 1 minus QR upon QS, where QR stands for heat rejected and QS stands for heat supplied. So 1 minus heat rejected divided by heat supplied will give you the efficiency, either in case of a diesel or Otto cycle in generally. Now we want to find out which engine is going to give you higher efficiency when the compression ratio remains same and heat addition also remains same. So now this is your Otto cycle. In this Otto cycle, you can see we have here constant volume processes, two constant volume processes, while here the heat addition process is constant pressure, while heat rejection is constant volume. Now what we are doing is we will be superimposing these two graphs into one, and we'll try to find out which one will give you more efficiency. So here we are saying that compression ratio remains same, and the compression ratio is indicated by line 1 2 1 2. So you can see when the compression ratio remains same, for both the graphs 1 2 line will remain same. Similarly, the heat addition is remaining same. That means the length of the line 2 3 is going to remain same. So 2 3 from here to here, or from here to here, or from here to here, it is going to remain same. If it goes like this is Otto cycle corresponding to constant volume, and this horizontal if it is diesel cycle, so it is going from here. So 1 2 3, and from here to here, 4 to 1, it becomes your Otto cycle, and from here 1 2 3 dash, from here to here, and then 1, it will become your diesel cycle, and obviously the dual cycle will be intermediate. So clearly we can see that with Otto cycle, that is 1 2 3, in this particular curve the maximum pressure is obtained with Otto cycle, and corresponding to maximum pressure, peak pressure, maximum temperature is going to attain, and when the temperature is higher in the cycle, obviously the work output is going to increase. So so we can say from PV diagram that Otto cycle is going to be more efficient. Now with the help of TS diagram, let us see which is going to give you more efficiency. Now here this 1 2 was same and 2 3 was supposed to same. Here also 1 2 is same and 2 3 is going to remain same. Now this 2 3 is constant volume, and here 2 3 dash is going to be the constant pressure. Like the is different than this is more steeper, and correspondingly this particular line corresponds to 3 4, where we have during 3 4 the expansion takes place. So here 3 4 and then 4 1. So 1 2 3 4 1 is your Otto cycle, 1 2 3 dash 4 dash and 1, this is your diesel cycle, and obviously this will be your intermediate. Now here the efficiency of any cycle will be given by 1 minus QR minus QS, and this efficiency will be higher when QR by QS, this particular ratio is going to be smaller, because this is 1 minus this particular ratio, and if whenever this ratio becomes smaller, the efficiency term becomes larger. That means this fraction has to be smaller. So if you want to make this particular fraction smaller, then numerator has to be smaller or denominator has to be larger. So either of this will be able to ensure that the efficiency is going to be higher. That is a numerator, a smaller numerator or larger denominator. But here what we have said, heat addition is same. That is QS is going to remain same. No therefore the QR is only probably now going to change. And when we observe here the QR, the heat rejected, the 4.1 is the heat rejected in case of Otto cycle, and 4-1 is the heat rejected in case of diesel cycle. Obviously Q41, which is the heat rejected in case of Otto cycle, is going to be smaller. So when numerator is smaller, then the fraction becomes smaller. So compared to the diesel, this ratio QR minus QN in case of Otto cycle will be smaller, and therefore Otto cycle efficiency is going to be higher than that of diesel cycle. So the correct answer will be the third one, that is Otto cycle efficiency is greater than dual cycle efficiency and is greater than diesel cycle efficiency, because the dual is going to be intermediate that of here also, and here also you can see it is intermediate that of Otto and diesel. So Otto will have the maximum and diesel will have the minimum efficiency in this particular condition, that is same compression ratio and same heat addition. Similarly here also we are comparing the Otto, diesel and dual cycle with the same compression ratio and same heat rejection. So now here 1, 2 is going to remain same, that is the compression ratio is going to remain same for both the cycle, and heat rejection, that is 4.1 is going to remain same. So 4.1 and 1.2 are going to remain same. Now obviously as we know that in Otto cycle this is heat addition is constant volume, here it is constant pressure. So the constant volume 2, 3 corresponds to Otto cycle. So Otto cycle corresponds to 1, 2, 3, 4, 1. And the diesel cycle now is 1, 2, 3-4, 1. Obviously 1, 2, 3 will have 1, 2, 3-4 loop will be having smaller area, and higher area means corresponds to higher work output. That means the efficiency is going to be greater in case of Otto cycle in this case also. Similarly, if you look over here, then in TS diagram what we can see in this particular case, the 4.1 is going to be constant for both the cases, and 1, 2 is also going to remain constant. Now this is 2, 3 which is constant volume, and 2, 3- is constant pressure line. Obviously here 2, 3 is going to be longer than 2, 3-. That is the heat addition process is going to be more, heat added is going to be more in case of Otto cycle when compared to that of diesel cycle. So now again we want to check out which one is bigger, that is we want to have this particular ratio smaller. So if this we want to smaller, then what we want that is, in order to make this particular ratio smaller, either numerator has to be smaller or denominator has to be larger. Now which one is larger? Otto cycle, this is heat added QS is going to be larger in case of Otto cycle, and QR is going to remain same. So since the denominator is larger, this particular fraction for Otto cycle will be smaller, and therefore Otto cycle efficiency is going to be greater than that of diesel cycle, and obviously dual will be intermediate of this. So the correct answer is Otto cycle efficiency is greater than dual is greater than diesel. That is A is the correct answer for this case also. Now the next is time loss factor in actual cycle is due to. So here we are talking of time loss factor. So now let us see what this particular time loss factor and how it is coming into picture. Now here we can see 1, 2, 3, 4, 1. This is your that is 1, 2, 3, 4, 1. This is fuel air cycle, and 1 A B C D 1, that will be your actual cycle. So now how this particular actual cycle is coming into picture. If we assume that theoretically we are giving the spark at TDC, that is corresponding to 0.2. So if we give the spark at TDC, we know that theoretically we have assumed that the burning is happening inside the combustion chamber instantaneously. But if you consider it is instantaneously, that means this line will the vertical, that is 2, 1, 2, 3, this particular line will be the line for heat addition in case of the cycle. But actually we know that the combustion is not instantaneous. It will take some amount of time because the spark is going to form a nucleus of flame. That particular nucleus has to generate a complete flame, and then the flame has to travel throughout the combustion chamber, consuming all the fuel. And all these things will require some amount of time. So if we are giving the spark at a point 2, then we can see that the mean maximum pressure point has come down a lot. And so in order to increase the work output, what we do is, instead of giving the spark at 2, we give before 2, sometimes before 2. That is, in this particular case, we have seen that it is at A. So if we give the spark over here, during this particular time, the nucleus will be formed and the nucleus will be converted into flame. And by the time it reaches TDC, a full-fledged flame is going to develop. And as the flame is proceeding, the piston is moving back towards BDC, and the curve, this curve we get corresponding to the burning of the fuel. So here somewhere we have the starting of the flame, that is ignition has happened, and progressively the burning combustion happens, and here somewhere it is going to combustion is going to end, and therefore we get a curve corresponding to like this in case of due to the progressive combustion. So and this particular loss, whatever we have over here, this hatch line and this hatch line, is what we call as a time loss factor, because we have earlier time ignition. So the spark is given earlier, and therefore this particular losses are corresponding to earlier spark, and therefore this losses are called as time loss. So the time loss factor is in actual cycle is due to progressive combustion is the correct answer. Heat loss through the cylinder wall is not correct. Gas leak or friction is also not correct. So the correct answer is progressive combustion. So due to progressive combustion, we have time loss factor.